Okay, so this is lesson 2 of Unit 6. Unit 2 is all about quadratic functions. Today we're looking at quadratic functions in a different form. We'll be looking at them in vertex form. So vertex form is basically something you already know. As long as you know your function transformation rules, this should fit right in with that. So let's take a look at it as kind of an abstract graph. Here we got a limited domain. It just makes kind of like a sickle shape, okay? And we're going to look at some basic transformations that we've studied. So this is the graph of f of x. Well, what would the graph of f of x minus 3 be? Well, f of x minus 3, since the minus 3 is on the inside, and as we always joke, insiders lie, this is going to shift 3 to the right. Remember, inside the parentheses is left and right, but it's backwards of what you think. So we're going to move every point from here 3 to the right. So from here it's going to move 1, 2, 3. This point here will move 1, 2, 3. And then this 4, 2 is going to move 1, 2, 3. Let's see here. 2, negative 1 moves 1, 2, 3. And that's pretty much all we need, I think. And that's it. Next we have f of x minus 4. When you have minus 4 on the outside, it's a shift up and down. And it is the way that you think. Outsiders that are minus go straight down. So f of x minus 4, we're going to take each one of the y coordinates from the original graph, and we're going to just simply move it down 4. So I will lightly sketch the original, and then we can see how we transform it. So the first one was 2, negative 4, 0, negative 2, 2, negative 1, 4, 2. Then we'll make the transformations. So shift down 4. 1, 2, 3, not quite there. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And there we have it. All right, on letter C, we'll be doing a couple transformations. We'll be shifting 1 to the left and doubling all the y coordinates. So again, let's start with the original. So we're going to shift 1 to the left, and then we're going to double the y coordinate. So it's going to be all the way down here at negative 8. Sorry, it doesn't fit. Shift 1 to the left, then double the y coordinate. So double the 2, making it 4. Let's take this value here. Shift 1 to the left and double it. Negative 1 goes to negative 2. Shift 1 to the left and double it. But remember, it's curved on that part. So you can see there's been a vertical stretch. Okay, let's consider example 2.2. We're given a graph of f of x is equal to x squared. First, let's graph x squared. Okay, so y equals x squared. 0 squared is 0. 1, when I'm plugging in an x value of 1 to y equals x squared, or f of x equals x squared. 1 squared is 1. 2 squared is 4. And then 3 squared is 9. So this just goes up like this. But those were the points that we were able to plot. And then negative 1 squared is 1. Negative 2 squared is 4. So it goes up like that. Okay, now we're going to graph this function. This is in vertex form, or what some people call transformational form. So we know that on the inside of the function, this is an insider, so it's going to shift 3 to the left. And then that's an outsider, so it's 2 down. So we'll take each one of these points and move them. 3 to the left and 2 down. Then we'll take that point, move it 3 to the left, and 2 down. We'll take this point, 3 to the left, and 2 down. 2, 4 moves 1, 2, 3, 2 down. Negative 2, 4 goes 1, 2, 3, and then 2 down. And we'll graph. So this function here has a vertex of negative 3, comma negative 2. And you'll note that that can be seen in the equation, that the vertex is the opposite of that number for the x-coordinate, and then that number for the y-coordinate. So that's why this transformational form is also called vertex form. Also take note that this stretch here from this one move over is a length of 1, which is that value. If this had been a stretch of 2, it would have stretched up more. Okay. So what I'm going to ask you to do is to try and graph, again, x squared. Try not to look at the example above. You should have the graph of x squared memorized. You'll be able to generate it quickly for points 0, 1, 2, negative 1, negative 2, negative 3, that kind of stuff. And then use that graph and graph your transformation. All right, let's see how we did on this. So 0 squared, this is the parent. 0 squared is 0. 1 squared is 1. Again, I'm just looking at the x values. 2. 2 times 2 is 4. 3 times 3 is 9. That's off the chart. Negative 1 squared is 1. Negative 2 squared is 4. Negative 3 squared is 9. Again, up here somewhere. Let's do our transformations. All right, this transformation has got 3 of them. We're going to move 1 to the right. We're going to move 4 up. But we're also going to have a flip. And the order matters. So you want to follow order of operations. We start with inside parentheses. So we're going to move 1 to the right first. Then we're going to flip the y-coordinate. Then we're going to shift it up 4. Okay? So we'll move this point here, 1 to the right. We'll flip it over the y-axis, the x-axis, which is still just 0, right? Then we'll move it up 4. Right there. Let's try this point here, 1, 1. It is here. Move it 1 to the right. Reflect over the y-axis, again, the x-axis. Then shift up 4. 1, 2, 3, 4. Let's try that point. Negative 1, 1. Move 1 to the right. Reflect down to negative 1. Shift up 4. 1, 2, 3, 4. All right, we'll do this point. 2, 4. 2, 4. 1 to the right. Reflect down to negative 4. Shift up 1, 2, 3, 4. Okay, this point here at negative 2, 4. 1 to the right. Reflect down. Shift up 4. But let's make connections to the vertex form here. This point here, the opposite of it, comma that, is my vertex. Right there at 1, 4. Then this negative 1 tells you how you need to move as you go left and right. So if I go to the right 1, I go down 1. Down 1 because of that. To the left 1, I go down 1. And that gives me, so I can see all 3 of those points from the vertex form, which is usually enough to get a good sketch, right? So you can see how we're going to move towards not doing all the points like I just did there, but by doing just what is necessary to get the shape. All right. A quadratic function of the form f of x equals a times x minus h squared plus k is in vertex form because the vertex of the parabola can be read easily from the equation. The vertex is the opposite of that number. That's why it has a minus h. Vertex is usually described as the h comma k. We'll state the vertex, domain, and range of each quadratic function. The vertex here is the opposite of that number, comma that number. That's the vertex. Next, we need to figure out the domain. So ideally, we want to be able to determine the domain and range just from looking at the equation. The domain is not very difficult because we know there's no square rooting, there's no dividing, and we know those are the things that cause problems. So our domain is negative infinity to infinity, or you can say all real numbers. The range, let's draw a quick sketch of what's happening to help us decide that. And eventually, hopefully, we'll be able to just determine it in our mind. So this is a parabola with a vertex at negative 6, negative 4, which is somewhere over here. The number here, what we call the A, is a positive 1, meaning that the graph is going up 1 over 1 and up 1 over 1 on both directions, meaning the graph goes like that. So you can see the y values are going upwards when the A is positive. So my range has a lowest value of negative 4, the y coordinate, and a highest value of infinity. All right, let's take a look at letter B. Oh, I'm about to draw a sketch again. Well, let's just start with the vertex. The vertex is the opposite of that number, comma that number. The domain for all our parabolas is negative infinity to infinity. And then again, let's take a look at just a quick sketch of what this might look like. Negative 1, 5 is somewhere over there. But notice that the A value is now negative, so it's going to be going downwards. It'll be a little steeper and a little more downward and going downwards. So this, instead of having a lowest point, has a highest point and goes down to negative infinity. So the range starts at a negative infinity and goes up to the y coordinate 5. Remember to use negative infinity. If you're using it, has to come on the first number, and it always has a parenthesis. And then we put a bracket around the numbers that we actually reach. So if you would please try practice 2.2, A and B. A little hint here, this might help if you realize that this G is written like that. That might help you see that there's no horizontal shift to the vertex, so we could still call that vertex form. All right, give that a try, then we'll go over 2.2, and then we'll do 2.3. Okay, let's see how we did. The vertex, once you realize that when there's nothing in parentheses, you can think of it as not being shifted at all left or right. You can think of it as being written like that, was 0, negative 5. This function is got a negative in front of the x squared, so it's opening downward. So it has a highest value. Domain is negative infinity to infinity, but the range has a highest value of 5, a maximum. All right, let's take a look at letter B. Go ahead. Oh, that's not right. Okay, thank you. This is 0, negative 5. I don't know what I was looking at. I wrote vertex negative 5 and I plotted it positive 5. All right, thank you for that. Okay, let's take a look at the next one. The vertex is negative 6, negative 7. Remember the opposite of that number, and then that number stays the same. This one is, so it'll be somewhere over here. And it's opening upwards. Very, very narrow, very steep, opening upwards. So it'll be a domain, of course, of negative infinity to infinity. But the range, we got a smallest value. So we're actually going to start with a bracket this time of negative 7. Notice they're always y coordinates up to infinity. Okay. All right, for practice 2.3, what I'd like you to do is think back to your transformations now and describe what effects these transformations have on the graph of x squared. And try and list them in order. So you should work from the inside out. Describe left and right shift, whether it's flipped, whether the y coordinates are stretched by a factor or shrunk, and then shifted up or down. Okay? So do practice 2.3, and then we'll go over that. Okay, so for practice 2.3a, we should have said that we would shift left 6, and you could say scale by 1/2, shift by 1/2, multiply the y values by 1/2, shrink or expand, whatever you want to do. So I'm going to say stretch by 1/2. And that just means I want to take all the y, so it would actually be condensing, right? But we're going to take all the y values and halve them. If they're and then we will shift down 1. All right, so on this one here, we're going to move to the right 1. We're going to reflect the y values over the x-axis. Reflect downward. And then we'll stretch by the y values by a factor of 2. This is going to shift left 1. We're going to stretch the y values by 2. Then we'll shift up 5. This one here is simply going to reflect over the x-axis and then shift up 10. So compare and contrast the graphs of f of x equals 2 times x minus 4 squared minus 3 and g of x equals 2 times the absolute value of x minus 4 minus 3. Let's think about what similarities do they have and what kind of symmetry. So the similarities here, think about that, how they're transformations. You should be able to graph each of these with equal ease if you understand the parent function of each. The graph of y equals x squared is a parabola that gets steeper and steeper. The graph of the absolute value of x makes this v. Other than that, these two graphs will have the exact same features of symmetry. They'll have the same domain. They'll have the same range of all y's greater than or equal to 3. They've all been stretched by 2. They've all been shifted to the right 4. The only difference is the parent function that we use to have those points that move left and right. So knowing our transformations allows us to have all this knowledge readily available.